8 people are there. This Kavita Mannaru? Kavita Mannaru is your candidate, no? Bye.
Oh, hi. Hey, hello everyone. How are you?
Good evening, sir.
Good evening.
Good evening, sir.
Good evening, sir.
Evening. Hey, give me just a minute, and meanwhile, I request all of you to please turn on your cameras. I will
Hi, sir.
just
Good
take a
evening.
minute. Hey, good evening, man. Arthur, nice to meet
Yes.
you.
Hi, sir.
And Clinto, nice to meet you as well. And Harsh. Oh, hey,
Good
Good
Harsh.
evening,
evening.
sir.
Hey, good evening. And Arshita
Good evening,
and
sir.
Ankit. Hi, good evening. And Rajit. Hi, hey, I remember from my previous class.
Yes, sir.
Hi. Hey, Adit. Hello, Subhanshu.
Good
Hey,
evening, sir.
Kavita. Good evening. Hi, Kundavi and Sujan. Nice.
Hi, sir.
Hi. Hey, Saivamshi. Hello. Oh, he just went off. Okay. Hey, Vikas. And Subhash. Nice to meet you. Yeah, just sorry I got distracted. I just also want to connect on my other device so that it would be a bit more easier. So we just have a few more folks that need to turn on your camera. So there's Sai Vamshi, then I think Gajendra. Hi, hey Sai Vamshi, good to see you. I know it's okay to be on the phone. Still, if I can see your face, it's much better. Hi, hey Elsa, hey Gajendra.
Hello, sir.
Hi. Okay, let me quickly. Now is the thing. For you may hear some echo just for a brief second. Please ignore that. Hi, hey Shivam, and we'll get started. Sorry. Okay, that's good. Now I am connected on my other device as well. We're in business. Okay, great. Hey, thank you guys for showing up. So what I understand is you've now completed a milestone, at least for the folks who have been doing this for a while. So what you have finished is a kind of good overview and good training on analog circuits. Not analog circuits, it's not yet designed, but at least I'm hoping that you're now comfortable with working with circuits, applying Kirchhoff's voltage law, current law, various op-amp related stuff where we understand that generally if the op-amp is working well and in negative feedback, then the input to the op-amp is nearly zero, and so on and so forth. And that helps us make some really interesting op-amp circuits. And then there's, of course, transient responses and all those. So I assume that you are reasonably comfortable. If you do need to refer to some of that stuff again, you can go back and keep reading it. Now we are going to, change focus just a little bit. We are going to now start to talk about a slightly different topic, which is two things actually I will cover. I just want to give a brief preview on the art of design. Now, the art of design is something that you will find that is not something that you can learn in a lecture in one day, but I would like to share a framework that will help you think about it and keep on practicing it. This is something you will get better over time. Okay. And this is something some of you will absolutely love doing. Others will take some time to come, and then I'm sure then sort of love it, because all of us, I think, love to create things, love to create wonderful things that are the best. So the art of design is how do we make these really complex and beautiful things that work really well. In our context, these things are going to be circuits, VLSI circuits, right? Designs. So first I will cover this art of design, and then we'll start talking about digital logic fundamentals. Now we'll really start from the very basic. The reason is that, we have quite a mix of students. So just in case you feel like something is really easy, that's good, right? That means that's good stuff for you. You can, of course, focus on the next lectures and so on. But um, if it's not easy for you, then that's okay as well. So, but I wanted to make sure we start from, how do we say, from ground zero. We'll not assume that you've learned something or not. If you have, then that's a good thing. Okay. So the very first thing, let me start go with. So what is design, right? So basically, a design is your solution, okay, to a practical problem. That's what a design is. So when you see a problem, you devise something that solves that problem, right? That solution, what you made, that thing, whatever you created to solve that problem, that is your design. Okay. And so you can see immediately that a design is something personal. Design is something you have made or a team has made, right? This was not something standard. So hence, because, it has this element of how do I say that, personal effect or personal character to it, right? So this is not something I can say that, oh, there is only one way to do it and this is a correct way. No, there are always many ways to do it. Each way has its own, call it, up and down. So it's like the best way I can say it is, hey, you ask someone to make some food, right? Maybe just an example, like in South India, let's say you ask someone to make sambar, right? It's a dish, it's a cook, right? Every cook will design it differently. I'm saying design, okay, cook it or make it differently, right? Is there only one best sambar in the world? No, there are definitely terrible sambars and there are good sambars. There are really good ones, but it's also personal sometimes, right? That some people may like some and not others. Design is something like that too, right? Of course, there are many basic things that at least it's very easy for us to check. Now, design has a design goal, right? There was a problem you wanted to solve. First of all, does it solve the problem, right? If it doesn't solve the problem, I would say the design is not even counted. It's a broken design. You need to go fix it. It's not yet solving the problem. It's a good attempt, but it's not yet a design. It becomes a design when it actually solves the problem, right? Now, the second question we will ask is, hey, how good, how well is it solving the problem? Is it solving the problem in all cases? Is it sometimes solving, sometimes not solving, right? Is it 100% of the time, a million times, no matter how much I try, it will always solve the problem, right? That means it's effectively solving the problem. So that tells us how good or how effective is a design, right? A second thing is it efficient, right? Maybe to solve a problem, right? Maybe the problem was, make a device that can add two numbers, right? Let's say, right? And you know what you did? You said, hey, look, I'm going to buy a calculator and I'm going to give it to somebody and say, look, here is a device. It can add two numbers. Someone says, hey, I'll take a supercomputer and, or, a very expensive workstation and connect it to a very complicated monitor and everything, have a fancy keyboard and so on and so forth. That can add two numbers too, right? Both are solutions, both work, right? In this case, both are solving the problem, but one is much more expensive and may or may not be needed, right? And the other one does it, I would say, a bit more efficiently. So efficiently means how effectively or efficiently are you solving? Are you using low power? Are you using less hardware, right? Are you doing it in a smaller space? Is your solution going to be light, right? Is it easy to carry around, right? Or is it really complex? So this is another way. So we can measure a design in terms of its efficiency, okay? Then how cost effective it is, right? It may be that the design has very less components and is very small, right? But it could also be very expensive, right? Whereas the other design may be a bit bigger and crude. Maybe it's using, cheaper, older technology stuff. Sometimes that can happen, and it may be cost effective, right? So while efficiency and cost effectiveness usually go hand in hand, sometimes they may diverge a bit, right? So that's why I'm saying that's another metric by which you can evaluate a design. how robust it is, right? How good is it working? Like, for example, if I change some things, if as an example, if the temperature becomes really hot, will this electronic circuit stop working, right? If I put it inside water, will it stop working, right? If I, I don't know, do various things to it in all conditions, right? How good is it working? If I keep on throwing data at it faster and faster, up to what speeds or up to what extent it works. So, and also how robust it is. Like, if there is a bunch of noise, there is, a difficult environment, right? Is it still able to survive and do the right thing without making mistakes, right? That means it's very robust. Then a next thing is, hey, great, it does this problem. It's really robust, cost effective, and efficient, which is awesome. And hence it's being used. But is it something I can extend? Is it reusable? So for example, I make a solution that can do something. Can I use the same principles and extend it to do more and more, right? That is another metric. Now, just like in real life, right? So please don't expect your design to get A plus on everything, right? And it's not required as well, right? Sometimes you're designing it to be really best in class, right? Most low power, it's going to just consume next to nothing power or something, right? Or you're making it really light. And in those cases, right, you may end up making it more expensive, or you're making it really, really fast, the fastest circuit to do something, right? Now, in this case, you may end up making it more expensive, right? But then this circuit does it very fast. And because that's something that you are pushing for, right? So there's always trade-offs, right? So please don't assume that, we always need to make a design that is the best in everything, right? Sometimes it's not even possible. You do have to make trade-offs. Why? Because this is not, how do I say, a classroom situation, not an ideal situation. This is real life, right? And here we do have to make trade-offs. Sometimes you have to give up something to get. So sometimes you have to put more cost, more hardware to make it faster, or add more, consume more power to do something to reduce errors. All these things. I'm not saying that there's almost always a trade-off, and there's always innovative ideas that push that trade-off, right? That means for everything else being the same, you do it lighter, faster, lower power, better, right? And that's how the design keeps improving. So I just want to let you know. So please always remember this. Now what you're learning, right, in this course is how to understand the basics, the fundamentals. But why are we learning these fundamentals? We are learning these fundamentals because each one of you will, I'm hoping, will become a designer, right? Will become a circuit designer of some sort, VLSI designer. It could be a digital design or analog, whatever be the specialization, right? There are so many, and we'll talk about those later. But each of you will become a designer. So then always remember that this is the fundamental of design. This will apply to any designs that you make. First, the design is your or your team's solution. You may be part of a team where there is a captain or a leader, right? Or you may be the leader, or it may be a single, like it may be just your design, not a team design. All of these are okay, but remember it's your or your team's solution to a specific problem. So please don't tell me you have designed something and you don't know what the problem is. That doesn't make sense, right? Because you should definitely understand the problem really well before you make a solution. Because how do you solve the problem without knowing what the question is, right? That is doesn't make sense. So, and you should be always thinking about, okay, how does my design work across these metrics? After some time, this will become habit, and then you won't need to practice this. But until it becomes a habit, right? I will I will tell you what I want you to follow. Unfortunately, you have to follow this through the rest of this in doing homeworks and design. So what it is, right? So I call it a design thinking canvas. Okay. So there are 6 steps that you will follow to try to solve any problem. It may seem like extra steps. It may seem like you're writing more stuff, which is okay. So what I want each one of you to do, right, after this class, of course, take a new, it could be a recycled notebook, it could be anything, but you need a separate book, right, a separate notebook or diary of some sort where you can write, okay, and reserve this just to doing this, okay. What we will do is each It could be a single page, it could be a few pages, but try to solve a problem or a design in a few pages, and we'll break it down by these metrics, and you have to write down exactly all 6 metrics. So when I ask you for a lot of design problems in homework, right, we will insist that I want to see all the 6 steps. I want you to keep practicing this until this becomes a habit. So what are the 6 steps, right? So the first step is problem summary. Once you write down a clear problem summary, this tells me how good you have understood the problem. If you didn't understand the problem while writing the summary, you can refer to it. You can research it. It's quite normal. Sometimes, we don't even properly understand the problem. And it feels like there's pressure to go, work on the design. Somebody is already ahead. Please don't worry about those things, right? Everybody has their own way of doing the design. You have your way. So, but please don't go to step 2 without understanding step 1, right? You must understand the problem really well and be able to summarize it. You don't have to, start working on the problem in this canvas, design canvas book, right? But you can work in your rough book. You can try all sorts of things, do your research, understand your problem. Once you have properly understood the problem, I want you to come to this design canvas, write the problem summary. Say problem summary. Below that, you explain what you're trying to do. What is the problem you're doing? Okay. So that's number 1. Step 2, right? It's really important. Of course, it's part of the problem itself, but we take it separately. What are the inputs and what are the outputs? What information I'm going to get and in what way am I going to provide the outputs, right? You should clearly mark this. There should be very, very clear diagram or clear list. These are the inputs I get. And first you write all this in English, it's okay, right? Later, as it becomes more specific to electrical things, you can try to, draw it, sort of write it in different ways, right? But first you write the inputs and outputs. What comes in, what goes out? What are all the inputs? What are all the outputs, right? Very easy. Then we come to step 3, conditions and actions, right? So probably you may have, understood or thought about it in the problem summary itself, but the problem summary will just tell something like, hey, I have these inputs, and based on this, I need to do this. So think of an example like, oh, I need to design a traffic light, or I need to design an elevator controller, right? Or, hey, I just need a simple counter that counts how many times a button is pressed, right? So in these cases, right, the problem statement is straightforward. Hey, look, the problem summary is, count how many times the button is pressed and try to avoid noise. So what is noise, right? So maybe, as I'm pressing, it's a mechanical device. Sometimes, it may, there may be a kind of spikes, like, like I hit it once, but maybe it just vibrated and you got 3-4 clicks. You don't want that, right? So that is called de-glitching. So you want to make sure that those kind of noises are avoided. Now, if the button is stuck, right, you want some ways to reset it and few things. So those will be, of course, part of the problem, but summary. But then the conditions and actions tell you that if this happens, then the mode changes. We are moving into that or something. It's more of, so basically the way we are saying is, number 1 is a problem summary. From 2 on, the details will be clarified. What are the inputs and outputs? 3 is the control responses, right? What will trigger certain things? Hey, when someone clicks this or presses this button, or when light shines, or when this sensor triggers, then you go into this mode, you start doing this other thing, right? Or when this other clock pulse comes or something, you do this next thing, right? So this, I would say, are conditions and actions. Think of more like control signals, right? These are specific events or triggers or things that happen. And when they happen, something changes in your design, right? Not in your solution or in the system. So you want to write those clearly, right? What triggers certain behavior? What should happen when this comes up, right? If something else happens, then what? And so on and so forth, right? So clearly write the conditions and actions, okay? And the fourth thing that you need to think about is memory and state. And all of these, right, will become clearer as you do more problems and so on. So memory and state means, there are certain things that you want to remember. So let's say you got inputs, you're getting a new input every clock cycle, right? and maybe you got 100 inputs because it's 100 clock cycles, right? But maybe you don't need to remember all the 100 inputs. You just need to know what state you're in, right? It's like, you have the lift going up and down, right? You probably need to know which floor you're on, right? Or from which floor to which floor you're going, right? If you don't know that, then it'll be very difficult to design a controller, right? So this is something you have to keep track of, right? So that is what we say we need a memory for, memory or states, flip-flops. We have so many memory elements, right? And we'll study about those. So you need to clearly write down what kind of memory or states you'll try to remember. And the fifth step, it's really straightforward. It's putting all these things together. You have the inputs and outputs, you have the controls and behaviors, you have what sort of memories you have. Here you sort of make a small sketch of the algorithm, right? Hey, this is how I'm going to do it. I do this first, do this next. There's an if loop here or if conditional here, then this happens, and I loop this over and over 100 times or n times, whatever that is, right? And then if this happens, I break the loop, whatever it is, and I come out and do these things, right? So this whole thing, you can use your own way of making your sketch or diagram. You can make it as a text, you can make it as a picture, whatever is comfortable for you, right? But this algorithm decides, this explains how you're thinking about your solution, how your solution is working, right? And we are thinking about this algorithm as at the moment your design solution. Okay, I'm not asking that you should write your, call it Verilog code or draw your circuit here or something, not needed. So long as you get at least up to a high level algorithm and put it there, that's a good solution. And then after the algorithm, this is also a very important step. You'd think that, hey, look, now I've sort of done my design, I'm done. No, step 6 is very important. So what does step 6 talk about, right? Step 6 talks about, sorry, one second. Yeah. So step 6 is talking about alternate ideas, reflections, right? So you have now found a way to solve this, right? How else could you have done it, right? What else you could do with it, right? Could you have done it in a better way? Is there a different way to do the same problem, right? This is very important, right? Thinking about this, right, doesn't mean that this is wrong, right? It doesn't mean that. All it means is that two things. One is next time you were to design it, right, would you do it differently, right? Also, what could be trade-offs? And this is a learning part, which is very important. That means at the end of your design, you must think, could I have done this differently? At least one other way you should think how you could have solved the problem, right? What were the trade-offs and why you picked one or the other, right? How could you improve this design in the future? These are the thoughts, alternate ideas. You write those, right? So every time you're given a design problem, this is what I want you to do. First, right, you need to go and make your problem summary. Okay. So describe clearly what is the design goal, what you're trying to do, right? Then clearly mark the inputs and outputs, right? Either you can make a little box and show these are all my inputs, these are my outputs, or you can make a list. You can say, hey, here is my inputs, and these are my outputs, right? And here is the list of things, and this is what they mean. If the names are sufficiently descriptive, you don't have to write more, right? I'm not asking you to write big essays, not required, right? Just write enough that it's very clear, but also, you don't need to overdo it. So, okay, your inputs are done. Similarly, try to explain some critical conditions and actions. Same thing, understand what memory and states will be involved. How will you save certain things, right? And ultimately, this is your solution, which is you make an algorithm sketch. Yes, this is not yet a design. The design itself is probably putting things together, constructing it, either making an IC or drawing some circuits or something like that. That is your design. But I would say, so long as you reach the algorithm step for now, that is good enough. That is already a solution. And then finally, without fail, I want you to think of alternate ideas and reflect on your design, what you think you did well, where you think you could have further improved, right? And if you do this, I would say many times, right, these will start coming naturally to you. So as soon as someone's explaining a problem, immediately you're trying to understand the problem. In your mind, you're clear about what are the inputs, what are the outputs, how am I going to do it, and all this will start coming to you, right? But until that point, I want all of you to please follow this 6 steps. So each of you must make this design canvas. Okay. Pick any notebook. It could be an old notebook you're not using anymore or whatever. Of course, it needs to have fresh pages, right? Or a new one, whichever is comfortable for you. And each design needs these 6 points. You can, write those in your own way, but they should be in this sequence only. And for each design, you should write all 6 and then move on to the next design. Okay, so please follow this, and several of the homework design problems, at least and I will request you to share pictures of this design canvas along with your solution. Okay, so clear on this. I know this is a lot of stuff and I've been talking continuously. Sorry about that. Any questions or any points from anybody? Okay, I didn't mean to shock you guys, but okay, you do need to
Sir,
follow these steps. Yeah, go ahead.
sir, you just show me the where we can write this the canvas or so that we can clear more about
Okay.
of this.
Okay, so I think the question from Jaskaran Singh, right? It's a valid question. He's saying, "Hey, can you give me an example? Can you show me how I would go about doing it?" Right? Very fair. So let me actually do this. Just a second. Believe it or not, I was actually writing or spending a time doing this. So let me see, what do I have here? Okay. I mean, this is, oops. Oh, first of all, let me clear all this junk from the screen. Okay, let me now start zooming. Okay, so let us say the problem is counting button taps. Okay, that's a problem. Okay, so then how would you do it, right? So problem summary, hey, we want to count how many times the button is tapped. If the button is held down or pressed too quickly, we should count it only as one tap. I mean to say, if there is vibrations or if there is like, too fast a tap, we can set what the time is, but we can say what is unrealistic and say if it gets tapped before that, I won't count it, right? And then the system should ignore noisy or repeated signals and only for clean and distinct taps. That means what am I saying that I should tap? It should be a decent gap. The gap can be anything. The gap can be 1 millisecond, right? And for humans, that may be too fast, which is okay, right? But some reasonable gap. And this is how you just describe the problem in plain English. You're not giving a solution. You're not trying to specify the problem like a specification data sheet or something, right? It's just a small paragraph. Of course, it's a very simple problem. So even the summary is quite short and simple, but I do expect the summary to be like this. Okay, what are the inputs I'm going to have, right? Okay, hey, the input is going to be a button signal. Something the button will tell me whether, let's assume 1 means when it's pressed, 0 means it's not pressed or something, right? And then I do need some way to measure time. Usually in electronic circuits, we have a clock and there's almost always a reset signal. We'll talk about all these signals. This is just my solution. You may have a slightly different solution. And if your solution didn't have clock and reset, but had something else, that's quite okay, right? Like I said, design is definitely personal, right? Personal in the sense, like I said, every chef makes the dish differently. In the same way, every designer is going to design it slightly differently. It doesn't mean any design is right or wrong. So the design is right or wrong just means when you solve the problem, how good is it solving it, and so on, right? Okay, so these were my inputs, and my output is straightforward. I just tell you how many times the button has been pressed. Why do I have a reset? So whenever reset comes, I'm going to reset my count to 0, and then I can start all over again. So that's why I have a reset. So that's it. So what are the conditions and actions? Okay, if reset is active, then forget about counting. While reset is happening, the count is forced to 0. That's it. Don't do anything else, right? Okay, if button signal goes from low to high, right? That means someone just pressed it, right? Hey, that means I should increase count, right? If button stays high, that means someone has just pressed it and forgot to remove his finger, or we are really fast. And as a human, maybe, the finger is not quite as fast as our clock. Then maybe running at megahertz or gigahertz, who knows, right? poor finger can only do seconds or maybe tens of hundreds of milliseconds, right? So yeah, do nothing. And then button signal is bouncing, right? Now, what is bouncing? This is an internal probably thing. But if you detect that it's going up and down too fast, that doesn't make sense for a human to do it, right? Which you think, according to your design, this is not real. I don't believe it. That means something else is doing this up and down. So I'm going to ignore it, right? Keep on ignoring those bounces. Don't count them as counts until it becomes stable, right? This is the one that's call it debouncing or denoising, however you want to think of it. It's getting rid of the noise, this kind of technique what I have. So this is how I have described my conditions and actions, right? What do I need to remember? Okay, I need to certainly remember the previous button state, not the present state. The present state, I have an input that tells me right now, is it high or low? Is it pressed or not pressed? But previously, was it pressed or not pressed, right? This is something I do need to know. And then what is the current count value? Certainly, we need to remember those, right? And then there may be certain states. Are we, idle? That means the previous and for a long time button has not been pressed, right? Or the button was recently pressed. And so maybe, you're looking for things like, did I press? Did I release? And then is this happening too fast or something, right? So these may be some states I need to remember. So these are all the things I want to remember. This is in my memory, right? And finally, what would be the flow chart? Okay, I have a silly flow chart. You can have your own. Like I said, right? This is just a solution I came up with. This may not be, please, this is by no means ideal or anything, right? So, hey, I'm in idle state. Button gets pressed. That means button goes high. Then I go to press state, then button goes low, then I go to release state, back to idle. This is not a full flow chart because I haven't shown what happens if, the noise stuff happens and so on. You can kind of write it like this. I would say I was definitely a bit short on time. I should have done a better job because if the debouncing I haven't taken care in this flowchart, it should be included. Okay, so this I will myself admit and I should fix it. So this is something that's missing here, right? And what are alternate ideas? Hey, maybe I could have used a timer to wait instead of a clock. Uh, uh, you know, and wait for a debounce period before accepting. The danger is that you may miss something or it may add delays. And an improvement is use a debounce filter using a small counter or shift register. There are some techniques. I didn't want to directly spill the standard solution, right? So, and there's a whatever thoughts come to your head, right? Just put it here. It doesn't have to be perfect. The main thing is you have to think about alternatives. Don't only think that you have only one idea and that's the only way to do it, right? This will help you think what are the other options, what else I could have done, right? And why I chose this method, and according at least to you, why this seems like a comfortable and the right trade-off, right? So this is just forcing you to sort of review your design, think about it, and think of other ways that one may solve the same problem. Okay, so I hope this kind of gave you a sense of how you can make this. Uh, and of course, right, I have typed it all in. You could write it in your notebook. You can whatever is easy for you, right? So just usually typing is more painful for sure. So you should be writing it initially, and that makes it easier. And you don't have to write out many things. You can use your own reasonable shortcuts that are understandable to others, right? Just make sure it's reasonably clear that someone can understand it. That's it. So that's how you do it. Any questions?
Sir, for this, like, we'll be given a problem set, like, for doing, or?
Yes. So let's say, and not just that, I'll give you a problem and say, make this canvas. I'm saying for the next few months, whenever you're given a design problem, right? Of course, I will try to remember to ask you to fill in the canvas and share your canvas pictures, right? But always make the canvas for any design problem. Now, as an example, if I say, hey, solve this thing, like, convert binary to decimal. That's not a design problem. That's just a question, right? So for that, you don't need this. But if I give you a problem, hey, design a controller for a lift, right? Or design a traffic controller, right? That's a design problem. So there you're designing a solution, right? So for that, you may have a solution, which may be a circuit or a flow chart or a diagram and so on, right? Which is your design. But in addition to the design, I want you to always make this design canvas. Okay. So I'm just preparing you for this in the sense, when we give you the problem, I'll just simply say, please also share me your design canvas. Then when I say design canvas, this is what I mean. And as a habit, I'm insisting for now and really requesting all of you to do this design canvas every time you design something. Okay. Of course, first thing, it's very empowering because you're designing. That means, please remember, it's your solution. You are making your own solution to a problem that you have encountered, right? You found that you need to do this. For whatever reason, this circuit is needed for this chip, then that solution you're making is your solution. So please make sure that whatever solution you make, right, you are, you're happy with it, you're proud of it. Please don't design things that you yourself think are junk, right? Don't do that. So this is something I'm saying not for now. I would say even 5 years from now, 10 years from now, whatever you design, please make sure you're going to be happy about it, proud about it. Yes, it doesn't mean that's the best way you can do it. You may learn more things and do it even better, and that's okay. But at the moment you designed it, so long as you do a good job, you feel like you've done good, that is good. Why? Because design is personal. It is specific to each individual and team that makes the design. Okay. Okay. Any questions on design and also on the canvas?
No, sir.
Yeah. Mhm.
No, sir.
No, sir.
No. Okay. Okay. Great. Hey. Okay. Super. So now that I have put all this, oops, wrong. Okay. Now random stuff is on my screen. Let me find the presentation. Sorry about that. I just have a lot of stuff happening. Here it is. Okay. So very quickly, we recap. Design is your solution to a practical problem. Each solution is, somehow like a craft. It's personal. Yes, it can be measured in many different ways, but there's no one only design. There's always better ways to design it, but then so long as the design solves a problem, it's a good design. Okay. And what I want you to do every time you do certain design problems. Now, like I said, this is not every time you get a question, you don't have to do all 6. It's when you design something. Okay. So these are the 6 things: problem summary, inputs and outputs, conditions and actions, memory and state, algorithm sketch, finally reflect on alternate ideas. Okay. And it's perfectly okay to, make mistakes, have wrong designs, misunderstand things, nothing wrong with it. The process of learning does involve making lots of mistakes. And that's how we learn as well. So we don't only learn by doing things correctly. Often we learn a lot by making mistakes as well. So that doesn't mean I want you to make mistakes, but it's perfectly okay if you make mistakes. Don't feel bad about it. We have all made many, myself included. So, okay, good. Now let's move on to the next topic. I know I sort of just talked about design. I haven't given you design problems. So why did I start on this weird topic of design? Because I want you to know, right, what a design is and what solutions are and how to think about it. So that whenever you encounter, maybe not the first class, but in a couple of classes, or at some point, slowly we'll start giving you design problems, right? When I do give you design problems, that's how I want you to do it, right? And a design doesn't only have to be a circuit design. A design can be writing code, right? You're writing a piece of code to do something, to solve a particular problem, right? To automate something, or that is also a design. Okay. So whenever you do these things, I'd be very happy if you can try to fill in your canvas with that, right? Explain the problem and all those other steps that went with it. Now we're going to switch gears. Now we're going to talk about circuits and logic, right? So you have already done circuits. So don't worry, I'm not going to test you on circuits. But I assume that you've sort of gone through that and it's done. And that was a different way of looking at things. So what we were doing there is we were given a certain circuit and we were trying to understand it, right? And that was about a very, very detailed level of understanding how the signals are moving, what are the transient responses, and so on. In digital, right, we're going to talk about literally only usually two states. Later we'll see about some other things, but let's say two states, just 0 and 1. That's it. So we just only talk about zeros and ones. So you'll say, hey, you're below something, that's a 0, or you're above something, you're a 1. So kind of like pass fail. It's not pass fail, true false. Right? These are binary states, two states only, right? So all our logic part is going to be based around this binary two-state type of system. So that's what we'll now be talking about and covering. This is the stuff that is quite possible that many of you may find it super easy. If you do, that's okay. And if you find it not easy, that's perfectly fine. And that's what we want to cover. So you have mastered KVL, KCL, transient response. Okay, now we are entering the world of ones and zeros. Okay, what are we going to talk about? So today's focus is going to be on Boolean algebra and CMOS logic. Okay, we'll first understand what are these number systems. Binary number system, decimal you're already familiar with, hexadecimal number system, and so on. And then talk about this thing Boolean algebra. What is Boolean algebra? Why are we so concerned about it? So on and so forth, right? Talk a little bit about logic gates. What are these logic gates or logic operators? Then we'll cover things like truth tables, Carnot maps, and combinational logic. We'll just keep going as far as we can. If we don't cover everything, we'll cover more in the next class. If we covered everything, we'll do more problems. So that's how we'll keep going. Okay. So let's get started right away, right? So first I want to cover number systems, right? So what are number systems? And a quick question for everybody. Who knows what is meant by face value? Can someone maybe, just give a try. Just tell me what is face value? Help. Of course, I have put it on the slide as well, but in your own words, right?
Radix
If you can
numbers.
yes, Mohammed, please go ahead one more time.
Radix numbers. For decimal values, we have 0 to 9. Those are
Okay.
10 number of values.
Okay. So,
And
so
for
for
binary, we have
example,
0 and 1.
for binary, it is 0 and 1. For
So
decimal,
the
it is
radix,
0.
the face value is 2.
Face value is 2. I'm
Not 2,
not.
its base is 2.
Base is 2. Yeah. The base, right? It's either binary. So face value, you gave good examples. For binary, you have 0 and 1. For decimals, you have 0 through 9. How about for hexadecimal? What face values would you have?
0 to F.
F. Okay. How
Yeah.
about for a number that is base 100?
Base 100. 0 to 99.
Correct. So of course you would have to write 99 with another character, right? Because then
Yes.
99 in base 100. So if I ask you to convert 99 in base 100 to decimal, what would it be?
Uh, Divided by 100. The number should be divided by 100. It's a bit more
I'm
complex, sir.
sorry, I had a bit of a disturbance. Let me turn off this one thing, but I couldn't get it. Can you please say one more time?
Sir, I think it's complex to me.
Okay, no problem. And we will kind of simplify it. Anybody else wants to attempt this, right? 99 in base 100. I want to know what is the decimal number for it. Okay, and we will certainly cover it, right? It's going to be quite simple. It's actually 9090, but we will see how it comes about, right? So, or sorry, it's going to be 909, but that's okay. We'll come to it. Okay. So face value, right? Face value means what are the possible single digit numbers in this number system, right? So they will always be start from 0 and they will keep on going up to n minus 1 for base n systems. That means if it's base 10, it will be 0 through 9. There will be 10 such symbols or characters, right? That will define 10 face values. In the decimal system, which we are very, very comfortable and we understand, we have 0, 1, 2, 3, blah, 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 9, right? And how many face values are there? There are 10. And by the way, Mohammed gave a very, very good answer. So thank you, Mohammed. Whatever you said was correct.
Thank you, sir.
And yeah, so there are 10 face values, right? So in hexadecimal, by the way, hexadecimal really stands for base 16. So in hexadecimal, how many face values do we expect? Anybody? How
16, sir.
many face values?
16.
16, sir.
Correct.
16.
Exactly. So we need 16 starting from 0, 1. So I'm familiar up to 10, right? I know 9. Now I need, that means 10 are covered. So I need 6 more face values, right? So what we do, right? What people came up with,
A, B,
I would
C,
say,
D, E, F.
yeah, they were not very, how do I say, creative. They just took the letters, right? They said, okay, you know what? I'm just going to call the letters and just call them as new numbers. I mean, they could have been really creative and came up with, new letters or whatever, right? But they didn't want to do that. Rather, they said, let's take familiar characters that we are familiar with and just add them to my number system and make it. So you now have 16 face values, call it 0 through 15, if you will, in a way, right? But 15 is now represented by this character called F. Why? Because we want only a single character to represent a face value. A face value is not going to be represented by multiple characters. It has to be a unique character. Okay, that is what a face value is. Okay, next we go into something else. So now maybe the question is, what is a place value? So maybe anyone else can please unmute and take a guess.
It's like
Uh,
zeros,
hmm?
10th, 10th and 100,000
Okay,
from
so
right
as
to
an
left.
example, yeah, so I'll just make up a number, right? So I think what you meant was this is a tens value, right? This is a ones place, tens place, hundreds place, right? This is how you were saying it, right?
Yes.
Thousands place, call it 10,000s place, right? Perfect. That's what it is, right? So basically we go from right to left in this way. We start with 1, which is also, and then we go to 10, we go to 100,000, 10,000, 100,000, we just keep going, right? And every time we sort of make it with more zeros, right? That's
It's
the
because
place value.
it's
Yeah,
because of base 10.
correct. So now a quick question, right? So this third digit, right, in base 16, right? What would you call it? Suppose the base was 16, it wasn't 10 anymore, right? And this, call it third digit from the right, this digit, right? In decimal,
It's like
sorry,
16 cube place. Sorry,
right,
16
right,
squares place.
16 squares. But would you still call it hundreds place? Would it be correct? What is 100 in base 16?
250, 600.
16 squared, right? So that's the cool thing about this place value, right? If I called it a hundreds place value, surprisingly, it works for all bases. Yes, 100 now means maybe a different number than what you thought in decimals, right? In decimals, it's 10 squared. And like Veera very correctly, reminded us, a hundreds place in a hexadecimal means 16 squared. It doesn't mean 10 squared. But luckily, it turns out it's still the hundreds place. It's just that 100 in hexadecimal means 16 squared. Okay, and 1000 in hexadecimal means 16 cube. It doesn't mean 10 cube. In decimal, it means 10 cube, but in hexadecimal, it means 16 cube, right? And what does 1000 mean in binary? Anybody?
2 cube.
2 cube, perfect.
2 cube.
Right, that's what it means. Perfect. So that's how it is, right? So there is this thing called face value, which basically means whatever be your base, there should be that many face values starting with 0, and you can come up with characters. Usually the convention is if it is 10 or less, please use the same characters that are already there in the decimal. If it's generally, hex or something closer, you just start adding text to it for new characters. Of course, there's no strict rule that it must be only characters, but there's a convention people follow. Of course, once you run out of characters, go wild, put Hindi characters, put Greek characters, put whatever you want, right? You can put more to add. But thankfully, we don't need to worry about those systems for now. So we'll focus on 3 number systems: binary, decimal, and hex. And I'll tell you why hex is important, right? But decimal is really important because that's what we learned everything in. We understand it intuitively. Like if you told me, hey, bring 100 grams of something, bring 100 pieces of something, it's very easy. I know to count it. I know to multiply, add, divide. I know to work in the system. I've learned it in school. It's down, right? So that's why, of course, that's our golden reference. But like as you guys already probably know, right? In computers, we store things in binary because each of the bits or pieces of information that we save can be in one of 2 states, 0 or 1, which means we can only store in binary. Unfortunately, natively, we cannot store in decimal, right? So we have to store in binary. So that's why the binary system is very important. It's very important to understand numbers in binary, okay? And then we'll also try to understand why the heck did we add hex? Maybe just to trouble you. No, not to trouble you. There is a use for it, and we'll come to it. So I hope right now everybody is very clear about face value and place value. Those are the 2 very, very important things I want you to understand. And the other thing, which is another weird or strange, not strange, but interesting thing, is whatever be the base, the place values are always 1, 10, 100, 1000. Yes, like, Veera reminded us, please be careful. The 100 is not a decimal 100 in base n. For example, in base 2, it is 2 squared or 4. In base 16, it's 16 squared. So what hundreds place means that exactly what's the value of 100 could change based on the base. But luckily, place values are just 1, 10, 100, so on and so forth. And yeah, so binary 0 and 1, and these are the name and place values. So let's just have some fun and quickly convert some numbers back and forth, right? So, oh, wait a minute. I have some answers already. Okay, so just let's take this number 101. It's a binary number, okay? And I want us to convert it to decimal, right? How do I convert a binary to decimal, right? So let's try to work it out. So I have 1, 0, 1, right? So what we do is we take the first number. It is basically 1 plus 0 into 2 power 1. It's actually 1 into 2 power 0, really, plus 1 into 2 power 2. That's what it really is, right? So it's very easy. So it is 1. Okay, this is also 1 plus 0. So ignore this, plus 4. So it's really 5 in decimal. Easy, right? I think I'm guessing most of you are very familiar already with this number system. So if there's any questions, we can go over this part again. So this is how you convert it, right? So for example, just for funsies, if I had a different number, right? Let us say I had a number 1001, right? Then what would be the binary? It'll just be 1 plus, we'll just keep ignoring zeros, right? And then this is a third place. This is 2 power 1, 2 power 2, 2 power 3. So 2 power 3, right? So it's basically 8 plus 1, it's 9, right?
9.
yeah, after a while, you'll look at these numbers and you'll already be able to tell that this is a 9, this is a 5, this is a 7. You just look at it and you'll know, which is okay, right? So this is how you convert from binary to decimal, straightforward. Okay, very good. Now let's convert decimal back to binary. I know I've been really silly and I took the same number 101 in decimal. I said, let's convert it back to binary and see what it looks like, right? So how do you convert this decimal into binary, right? What you will do is you just keep following this logic. You will take 101, you'll divide by 2 and find the remainder, okay? So the remainder is this. So you may have heard of this modulo operator, or that's the remainder. And then the dividend is this. So when I divide 101 by 2, I get a dividend of 50, or they call it quotient, right? Quotient of 50 and a remainder of 1, right? So I save the 1 and I keep 50. This 50 comes right back to the next row here. And then I do the same thing. What's the remainder when I divide by 2? It's 0. And what's the dividend when I divide 50 by 2? It's 25. I bring 25 back into the next row. I do the same operation. Remainder with 2 and dividend after dividing by 2. Bring this over, kind of keep going, right? So that's what we keep on doing. I have sort of done it for you. So please remember this number 50 comes right here. This 25 comes right here. So that's how the numbers keep coming here. So this is basically divide by 2, divide by 2. These are the quotients when I divide by 2, right? Until I run out of divide by 2s, right? And then how do I kind of get the number in binary, right? Oops. I just go like this. So the binary number is going to be 1100101. So this is the least significant bit. This is the one with a place value of 1, right? This is place value 10, place value 100, so on and so forth. And whatever will be that place value for this, right? So that's the binary number for 101 in decimal. Okay, this calculation is clear, right? Converting decimal to binary. Any questions? So we'll sort of go over the steps one last time because there are quite a few. It's quite straightforward only, but every time you find the remainder and your quotient, you put it in the next line. Then again, you always divide by 2, by the way. And you find the remainder and you put the quotient in the next line and remainder. And all the remainders are what make up your binary number. Okay, and of course, the first time you find the remainder, that is your least significant bit, or this is your call it place value of 1, right? And then the place value will just keep increasing as you kind of go down this. And this has your highest place value, or is the most significant bit. Okay. I think most people seem okay. Okay, so I will just move on, right? And we'll really now do a bunch of problems, right? Let's please convert all this to binary, right? I want you all to kind of do it. Maybe meanwhile, or let's do it as a class together, right? So maybe someone can unmute and help me do 54, right? I'm writing here 54. Just help me do this. So what is the remainder? Anyone can unmute and tell me.
It's 0, sir.
0. Okay, thank you. And then what should I write here?
27 mod 2.
Okay, good. And that is
1.
very good. And next line I should write
13 mod 2.
perfect. I'll skip writing mod 2s. Okay, what is 13 mod 2?
1 remainder is 1. Then 6.
Okay, then
0.
0,
okay, here.
3.
Very good.
1,
Here,
1,
here.
1.
So what is the number?
110
Perfect. Thank you very much. Very well done. That's this number, right? Very, very good. So now I want someone else. Oops, this went away. To help me with 37. So please help me quickly. 1 or 0?
18, sir.
18?
1. 1.
1. Okay. This is 18. Okay.
Excuse me.
0, sir.
Okay.
Zero, zero.
Okay.
0, 9.
Wait a minute. I think there was a question from somebody. Hold. Yes, someone said, excuse me. I think please go ahead.
It's not a question. I found a different way to convert from across number formats.
Okay. Okay. Let's take just maybe few minutes gap. Please go ahead.
So similarly, like we convert from binary to decimal. So we
Okay. Hey, you're on mute. Yes, go ahead.
similar to how we take 2, which is in like 2 in decimal, to convert from binary to decimal, right? So we take 2 to the power for like 2 to the power 2, 2 to the power 4, then we multiply whether it's 0 or 1 depending on the binary
Right.
position. We can take the representation of 10 in binary, which is 1010, and then we can multiply power. Like for 54 we can do
Excellent. So I think what you're saying, right, is that as an example, which is also a reasonable way of doing it, right? So I think what you're saying is, hey, look, 10 is nothing but 1010 in binary, right? And then I need to do 5 into 10. 5 is 101, right? In binary.
yes.
I multiply it and then I add a 4 to it, right?
4 times 1010 to the power 0.
Yeah, 4 multiplied by 1. That's okay. 4. This is 4, right?
And
So
1010 to the power 1.
Yeah, this is 1010 to the power 1
Yes.
right here.
Yes.
This 10. Yeah.
Yes.
And so yeah, you could do this fun math, and I'm sure you'll get this answer. And
But
just for
it's
fun, let's just do it, right?
it
101.
is very consistent.
No, of course it works, right? So
Yes.
1 into 101. 0 means, of course, all zeros. Then the 1, and then you add all this, right? Then what do you get? You get 0, 1, 0. Oops, 1 carry 1, 1, 1, plus 1, 0, 0, right? And you do this, I'm quite confident you should get this number, right? And it's reasonable, but you'll find that it might be more complex for us right now. And I'm saying, yes, it works, right? Of course it works. So good suggestion, Shivam. Nice one. Okay, let's quickly finish this, right? This, of course, I can do this really fast and convert it, and then you just put the remainders, right? So you know how to do this. Whoops, there should be 1 here. Yeah. So 100, 101. That's the next one, right? So in this way, we can convert. And yes, we could have done the multiplication, what you have said, right? And that definitely works. So, okay. So is everybody clear on how to convert decimals to binary? Right? Clear, right? Where you're able to do it.
Yes.
Okay, great. So we'll kind of, skip this. Now let's talk about hexadecimals, right? So of course we talked about the face values. We talked about all this A, B, C, D, E, F. Okay, that we learned in kindergarten. That's okay. And then we talked about place values, but why 16, right? Who came up with this 16 and why 16? It's basically a way to combine decimal numbers. Why? Because 16 is 2 to the power of 4. So what I can do is I can take 4 bits at a time and convert it to a hex. So please pay attention. Let's say I have this kind of 8-bit binary number. I kind of start dividing it into 4 bits at a time. 4 bits, 4 bits. So the first 4 bits are 0101, which I hope you can recognize as 5. Or if not, you can just trust me for it. Then the next 4 bits are basically 9.
9.
So what you will find is that this number in hex is nothing but 95. By the way, that's not decimal, right? That's a hex. So in hex, it's 95. It's really easy. Now, why is 95 better than this? As humans, honestly, we want to write fewer digits. We can handle 8 digits, I'm sure of it, right? But if I give you 16 or 32 digits and ask you to multiply a 32-bit number with another 32-bit number, you will find it dramatically complicated, right? Insanely complicated. I hope you can understand that. If not, give a try, right? Pick a random 32-bit number, try to multiply it by another 32-bit number, and see how well you do it, right? You'll find that it's insanely complex. At the same time, if those 32-bit numbers, right, could be reduced to more like, 8-bit. I forget 32, right? Take 16-bit into 16-bit. It's going to be very difficult. But instead, if I have a 4-bit number, 4-digit number and another 4-digit number, I could probably multiply it really well, and I could get the answer, and I could be reasonably confident about the correct answer, right? So this is what the hex does. It just reduces the number of digits by a factor of 4, right? So instead of 4 bits, you have to deal with 1 digit. Instead of 16 bits, as an example, you would have to deal with just 4 digits, right? Now, if I had a 16-bit number, as an example, that in hex ended up being, like I said, 4 characters, which could be 49A1, right? That's a 4-digit number. And if I had to multiply it by something else, let's say 2-digit number, or something, whatever it is. I probably won't do it right now, but at least this is something you could do it reasonably well and have good confidence, right, that you're going to get it right. It's just so we can understand things and read things really well. Because if I start writing 16-bit numbers, right, sometimes you will make mistakes in understanding, is this number same as, if I write it again another place, right? But instead, if I wrote something like, A451, right? And if I wrote, A451, immediately you'll recognize that these two are the same, right? But if I really had those 16 bits, right, and even if I write it the same, it takes us a bit more time. There's just too many numbers for our mind to, compare them and say they are the same and so on. So as humans, right, we would like to compact it and see less digits, right? And that's how hex came in. So hex is really for humans to deal with big binary numbers. That's all. Hex is not for anything else. It's really for us as humans to understand binary numbers better and not understand to be dealing with them, right? And can you think of a place where you may have seen this, right? I don't know if you have seen IP addresses, right? IP addresses, the V4 means there are 4 numbers. Believe it or not, they are in hex. They are actually 8 bits. So they are represented as 2 characters of hex. So you may find an IP that is, A1, 2567 bar, FF. I don't know if you would notice that you will never find any letters beyond F in these, right? It may feel like it's alphanumeric. It's not. It's actually a hex. Similarly, you will find this thing called MAC address, right? MAC address is an identifier for various hardware, right? Even there, you will find that it is mix of numbers and characters. But the curious thing you will find is that the character never crosses F. That's only because it's not numbers and characters. It's actually hex. Those are written in hex. They are just written that way, so it's easier for us to understand. The chip or the component really looks at it in binary, right? So the network or the hardware that is understanding this address doesn't understand it like this. It actually understands it as 8 bits, 8 bits, 8 bits, 8 bits, so it's 32 bits. It's a 32-bit number split across 4 sets, or if it's V6, then it could be another, 2 more numbers, right? But that's what it is. And so hex is just a way for us humans to better understand and deal with binaries, because very quickly the number of digits in binaries starts increasing a lot. Like if I want to represent even in decimal, right? Hey, I want to deal with 50,000. 50,000 is a number in decimal. It's normal for us. We can multiply, divide, work with it, right? But if I wrote that number in binary, it would be crazy. And for you to work with, those giant numbers is difficult. So then if we can kind of reduce it back to something with less digits, yet still kind of keep that binary character. How it keeps the binary character is because each character is literally 4 bits. That's what each character is. Each character is exactly 4 bits. After a while, you'll get really practiced. Immediately you see the binary, you'll be able to tell what character it is. If you convert 4 bits enough times, like you'll immediately recognize it. You may need a bit more practice to go A, B, C, D, E, F, those ones, but after a while, you'll start getting those, right? But that's really what it is for. So hex is nothing to do with design. Hex is there just for humans, okay? In design, in the chip, in the circuits, it's always binary, okay? So the only reason we learn hex is sometimes the same binary number, instead of confusing ourselves with many, many digits, we'll just deal with less characters, less things to write it. Okay, is that clear? Any questions? And I would really appreciate if you can also, keep your eyes open and see where else you may see hexadecimal numbers. And if you can, please report it next time. That, hey, I saw a hexadecimal number on this thing, right? Maybe it was something, a barcode for some things, like, you notice that some other things are also hexadecimal. That'll be kind of interesting. Okay,
Sir,
just,
I
yeah.
seen in televisions, like
Television,
when
okay.
there is no signal, it comes up like,
With the hexadecimal code.
yeah.
Yeah, it could be giving sort of an error signal or a message. And, the engineer would see that code and understand what he did. But brilliant. I think that's brilliant. Yes. So, and the reason, right, the engineer didn't print out the whole thing in binary is, I'm sure even he wouldn't recognize what that gigantic binary thing means. Because I'm sure if you put, 8 or 10 hex numbers, right, that becomes a very, very big binary string of digits. Excellent. Hey, good one, Veera. So please, yeah.
Wi-Fi routers, sir.
Yes, Wi-Fi routers.
Yeah, yes, sir. Backside of router
So
we have a code, and below that code we'll get that hexadecimal numbers.
Okay. And please try to find out what that code is for. Like, is it, the address of the router? Is it something else? What is special about that code? Is it the password? Is it a MAC address, or what it is? If you can investigate, that's a good one. Yes, router is another place you will see these hex numbers popping up, right? So thanks. So, okay, hey, so now we sort of got some idea. So I'm hoping you're comfortable converting these and so on, right? Of course, the reason we talked about all this is, from now on, at least from a digital design perspective, we'll always be working with binary numbers. To understand them, say from a human perspective, we may sometimes write them in hex, but almost always the systems that we work with, the electronics, it'll always be working on binary. Okay, so that is why just to
For color codes also.
color codes, yes, brilliant. Yes, so usually color codes are represented in the strength of each color, right? And very right, very much so. And each color, sometimes you may have an 8-bit or 16 or 32-bit representation of a color, and then instead of writing them out in bits, usually we write it in hex. Very much right. Very nice observation. And yes, those are hex as well, right? So hopefully now when you see the color codes, you'll understand them. Oh, they were supposed to be binary, but just so humans, we can read it and understand it, they get converted to hex and are shown to us. Of course, sometimes the IP addresses too, they sort of convert it to decimal for poor humans like us to understand, like 192.168. 0.1, 0.0, something like this, right? So of course, this 192 is a decimal number, and because the actual address is 8 bits, and it's generally, if you wrote it in hex, it would just be two characters, not 3. Okay, excellent. Now we'll move on to the next one, right? Next topic. Oops. Sample problems. Okay, let's quickly do at least a few, right? Otherwise later I can add some more to the homework. Let's pick this number, right? So this is excuse this complicated way of writing this number, but what this literally means in this context is this number is 75 and it is 75 with a base 10, right? That's what this means. That means this is a decimal 75 number. And the question is convert it to binary, right? This is very easy. We kind of just did it. So oops, 75, half of 75, 30, whoops, my bad, 74. So 37, I'm sorry. Half of 37, 18, then 9, then 4, 2, 1. 1, 0, 0, 1, 0, 1, 1. So the number is this thing, right? I hope you got what I just did, right? So let's have some fun. So this to decimal, I think this stuff you can already do. If you start to see this, you may notice that this number is 6, right? And this number is also 6, but with you can see that we have moved it 2, 4, it's 6 into 8, right? Honestly, this is a very bad way of doing it because this is not a consistent way. But I don't know if any of you remember, but we did 54 before and we did get 110, 110. You can do it in the same way or you could do it however you want, right? Like
Sir, can we apply 8421 code?
8421. Yeah,
Okay.
absolutely. Yeah, you could do that. So basically, this is 2, right? So 2 plus 0 plus 4 plus no 8 plus 16
Yes.
plus 32, right? You can do it like that. And that'll give you the answer as well. And we can quickly do it. So it's 20, 20 plus 2, 22, 22 plus 32, 54, right? Same answer. So of course, there's many ways we could have done it. Another way is like we said, hey, this is hex, this is 6 in hex, and this is 3 in hex. So it is 36 in hex. 36 in hex is very easy. So 3 into 16 plus 6, also 54. That was another way you could have kind of done it, right? This is a bit easier because now you don't have to do so many additions. You can sort of, if you can chunk them into bits of 4, right? You see that immediately you're getting speed up, right? Okay, this should be really easy, right? So convert this hex number into binary. So first of all, can anybody tell me what is binary for C? It's A, B, C, right? So this is like 12. Anybody? You just unmute and tell me.
1100.
Perfect, correct answer. 1100. Okay, what is the binary for 3?
1
1, right? 1, 1. Okay, so that's literally the answer, right? You can add zeros or you don't have to add zeros, that's fine. It's 8 bits, so we add it, right? Now, if I say, hey, tell me what is C3? C3 is hex, but I want the 8-bit, binary for it. So what would it be? Can someone tell me?
11000011.
Perfect. That's how it would be, right? Of course, when 3 comes later, please don't forget these 2 zeros. They are really important because you have to break them into 4-bit chunks, right? So, binary to hex and hex to binary, it's really straightforward. And that's why it is chosen like that, right? To help us make it really easy. Now let's do one more very simple problem at the very end. So the thing is, we need to do a hexadecimal addition. Okay, we'll do a very simple hexadecimal addition, A plus 5. How would you do it?
We need to
So
convert
basically,
binary.
Convert
with
decimal, sir.
Converting
yes,
into
you
decimal.
you can convert to decimal or you can go to first principles, right? So what is meant by adding 5? Adding 5 means after that number, I need to keep incrementing it 5 times, right? So after A, I just keep my hand, right? I have 5 here. So B, C, D, E, F. right? B, C, D, E, F. So, right. Of course, you're right. I could have done 10. I could have done 5. I could have gotten 15. I can then convert 15 into F. This is also a valid way of doing it. There is nothing wrong with it. So you can convert to decimal and back, or if you'd rather prefer, you could convert to binary, which is also straightforward. And back. So all of these methods are quite okay.
Sir, pardon me, sir.
Yes.
Sir, which is the preferred method to follow, sir, for this?
Whichever you like. So, so whichever you find easy at the time. So there's really no preferred. I would say if you're very comfortable converting decimal and back, go for it. But if you're converting, I would prefer you to. It depends, right? Depends on the digits. So since it's only one digit, you just convert to binary and back, right? If it's many digits, yeah, just think about how you do it. But whichever works for you, it's what you are comfortable with. Okay. Yeah.
Thank you.
And of course, a calculator is always a good option, but please don't use it unless it's if it's a homework problem, right? You can use it for otherwise when you're doing design and stuff. Okay, good question. Okay, so I hope now you're comfortable converting. You're comfortable doing simple math with these number systems, right? So we'll kind of stop with number systems and we'll go to sort of a next topic, right? So of course, please expect some homework problems to have these things as well. So these questions. So, but I hope everything is clear. Any questions on the topics covered so far, which is mostly number systems?
Sir, I have a doubt.
Yes.
I think we can't express A in decimal form.
Oh, no, it's very simple. A is 10. Yes,
Sir,
you cannot express it in
the
single
face
digits.
values are 0 to 9.
Yes. So you cannot express A as a single digit number, but A is really 10 in binary. Oh, sorry, did I say binary? Decimal. My bad. Right, in binary it is this. So yes, you cannot represent A in one digit, but you can represent A with 2 digits in binary. And you're correct, right? The reason you cannot represent A in a single digit is there are not enough face values in decimal to represent A. So that's a very good observation, right? So which means now you have to rely on your place value. So when you want to count anything beyond 9, right, then you need the next digit, like you go to 10, 11, 12, like that, right? So basically A is really 10. That is what I say. This is in decimal, and in binary it is 1010. So you see, I'm using four digits to represent a single, how do I say, character, right? In decimal, I need 2 in this case. Okay, right? You're clear that Y10 is A. Okay, good question. Okay, if no other questions, then we will proceed. Okay. So now we'll talk about this thing, Boolean algebra, that people keep talking about. So we already learned algebra in school, right? So what's this new stuff? Already it gave us headache when they talked about algebra in school. Now we're getting new headache with this Boolean algebra. So what is it, right? So let's actually switch topics. We start with something else. We say, okay, first let's understand what is logic, right? I think this is something maybe I'm hoping you will find it fun. So logic basically says, look, there are statements. Statements may be true or false, right? So a true statement, right? Like, hey, the sun rises in the morning on most days. Okay, so long as it's not sunny in that location, it's a true statement. On most days, the sun rises in the morning, right? And so a false statement, right? Sun shines brightly at night. Okay, that's kind of the opposite of night. Sun should not be shining at night. So if I say, well, the sun is actually shining, but we can't see it at night. So so that's a false statement. So the statements can be true or false, right? Now logic means I can now combine true and false statements into more complex statements. I can combine a statement like, hey, um, you know, I don't know, there are 10 I don't know, there is 100 kgs in a quintal and there are 10 quintals in a ton. This could be true or false. In this case, it's true, right? Because 1 quintal is 100 kg and 1 ton is 1000 kg, which is 10 quintals, right? So that could be a true statement. Or I could say something like, oh, 1 meter has 10 millimeters, or 10 millimeters is 1 meter. Of course, it's false statement, right? So I can say either 10 millimeters is 1 meter or 1 centimeter is 10 millimeters. Okay, I know it's a complex statement, but it's really a false or true. When you have false or true, it's actually true because at least one of them is true, right? Because that's how when you combine statements, you get the result. This is logic we are comfortable with, right? So when we combine two statements with a logical operation, right? In math, we call this an operator, right? Like previously for numbers, we had an operator plus or minus or multiply or divide or modulo. We had all these operators, right, that we used between two numbers, right? Similarly, in logic, we use operators like and, or, not, right? This happened and that happened, or that happened, or something or the other, and combine two statement into a bigger statement, which again can be either true or false. I can combine more statements and make this more and more complex, right? So basically, Boolean algebra is the study of this kind of logic. So why we worry with logic? Because the cool thing is logic works with binary states, true or false, two states, right? This is a binary number system. This is something that our circuits can easily work with, right? So that's the cool thing. And then the math, what kind of operations I can do, how can I combine a true and false with another true and false and get something else which may be true and false. How can I combine more and more of these true and falses together and get results, right? So all of that math is Boolean algebra. Okay, so doing simple statements is kind of easy. So in fact, before covering this slide, right, I would like to cover some examples, right? I know it's really silly examples, but okay. The stars are prominently made up of burning hot air. It's a true statement, right? It's basically so hot that it's all in gaseous format in stars, which is kind of like the sun. And so stars are predominantly made up of burning hot air. The next statement is the earth is predominantly made up of burning hot air. Well, that's not true, right? Earth is really made up of a lot of solid and liquids, right? And so it's not really gaseous from that perspective. There's a very thin skin of air around the earth. So, but it's not predominantly made up of burning hot air. So it's a false statement, right? Now imagine a statement like this. The stars and the earth are predominantly made up of burning hot air. Is this true or false, right? So turns out the stars are made up of burning hot air, but the earth is not. So how about this statement? The stars and the earth are made up of predominantly. It's a false statement, right? Because the earth is not. So that means true and false always gives you false, right? How about true and not false? The stars, but not the earth, are predominantly made up of burning hot air. This is true, right? Because the earth is not made up of and the stars are made up of. So true and not false is also true, right? Do you kind of see this? Don't worry, everything is not so complex. So from now on, I'll not be talking about all this hot air. We've had enough of that. But we'll just talk about true and false and combine them in various ways, right? True or false, true and false, true and true, false and false, all these combinations, right? So now maybe just for fun, I'll ask some questions, right? And you got to help me with it. So I'll just say T for true and F for false, right? True and false. Is it true or false?
False.
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 False. Excellent. How about false and false?
False.
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 How about not false?
True.
True, right? How about not false or false?
False.
True.
False.
Okay, true or false?
True. True.
Okay, so people are sticking to their thing, right? So, okay, what is not false? That's true, right? So what is true or false? True or false?
False.
True.
Right. So let's write into a statement, right? Either I am wrong or I am right.
True, sir.
I'm going to be either, yeah, it's going to be true, right? So usually if you combine a true or false, if it in or, right, what happens is even if any one is true, the result will be true. Okay,
True.
so of course this is working with kind of logic, right? So of course I can ask more questions, and but I see that you're kind of comfortable a little bit with this logic, right? So we'll kind of stop here. So this is logic. So in this, let me again bring your attention to some things. So let's say true or false equals true, right?
True.
Here or is a logic operator or logical operator. Okay, these are the two operands. It has two inputs or two, it operates on two statements, if you will, right? And combines them and gives a net result, right? So that's what a logical operator is. So now this is how we will understand things. Okay, so there is a thing called a logical operator. Logical operators or, and, not. Keep in mind, not operates with a single variable, not a, or not some statement, right? Not will not work with two. I have to say not this or not that, or not this and not. I can't just say not AB. That doesn't make any sense, right? So in this way, we have all these operators and they operate on, call it variables that can hold the value true or false. Variables could be things like statements, or they could be literally wires that can be true or false, which means 0 or 1, right? So that's what these operators are. So I hope now you understand what is logical operators. That's what they are. Not and, or, not and, not or. There's so many operators, right? So then what is Boolean algebra? Boolean algebra is the study, the math of this logical operators and logical expressions, right? Because what is algebra? Algebra is a study of numbers with operators and, you know, all sorts of expressions using numbers, solving missing variables, all those things, right? In the same way, everything is same, except instead of regular numbers, we are now going to be working with logical operators. Another way of saying this is really more suited for binary, things that work nicely with binary. And if you can think of them as true or false, right? So usually the simple operators that we talked about, right? We were able to easily understand and get the results. But as the operators get complex, right? Let us say I have an operator that operates on 4 variables at a time, right? You may find it difficult to intuitively tell the answer, right? You may need to work out the math to figure out what is the net result. If I say, you know, so that is the math that is called Boolean algebra. And that's what we'll be learning. And honestly, why we care, especially for digital design, well, I can't give you an answer right away, but hopefully it will become obvious as we start doing design. Okay, this is useful stuff. It's not useless. And it may take a bit of time for you to understand why we are learning this. But it's basically for us to be very comfortable working with things with binary state and lots of operators. And so we'll be very comfortable working with these, solving equations, using them, you know, doing all sorts of math with them. That's what is Boolean algebra, and that's what we want to cover. Any questions on Boolean algebra or operators or this logic stuff? Excuse me. No, right? Okay. Hey, I see most of you have turned on your cameras. I would prefer you turn them on, but that's okay. And thank you for all the rest of you who have kept them on. Okay, great. So now let's move on from this, all this stuff. Now, how will I define a new logical operator, right? Let's say we had a 2-input logical operator, okay? And okay. And then the main thing is when I'm defining what this operator means, it should be very clear. I cannot allow any confusion. It should be very, very clear. And ideally, if I can use the same format to explain more operators, to explain more things, it'll be nice because then I can work with a fixed format, right? Now imagine, we have things like lookup tables, right? Think of this truth table, right? What is this truth table? So basically, let's say I have a 2-input operator. Hey, Mohammed, you can mute yourself. Okay, so we have input A and input B, okay? And turns out each input being binary can have 2 possible values. So how many values can there possibly be for 2 inputs, right? Each input can be 2 values, 2 values. So basically total number of combinations is 2 times 2, 4, right? So we have actually written down all the 4 combinations, believe it or not. So there cannot be another combination which is not in this table, but possible with A and B, where A can be either true or false and B can be true or false, right? We covered everything. Then for each combination, we tell the result of this operator. This operator, it looks like false and false. Sorry, I should say and. False, false gives false. False, true gives true. True, false gives, and true, true, right? So this is and this way of representing or explaining how an operator works is called a truth table. Okay. So in this way, I can very clearly define how this operator works, right? There can be no confusion. Why? Because for every combination possible, I've already told you what the answer should be, right? So I don't have to write a math or write an essay about it. I tell you this table, then you can compute what this operator will do anytime, right? It's very easy. You just look up and you know the answer, right? Of course, this could be a familiar operator that some of you are familiar with. It's called exclusive or XOR. Also, what exclusive OR means is either A or B, but not both. That's, how do I say, a simplified English way of calling it, right? Later, you will find there may be operators that really have no good English way of calling it. Yes, there are some ways, but not so straightforward, right? So, but no matter what the operator, I can make a truth table. Now, a quick question for the class, right? How many possible 2-input operators, different operators can I have? How many different 2-input operators are possible? Can there be maybe, 1, 100, certainly more than 1, right? Maybe 10, or, I don't know, 8, 16, 32. How many, you think there might be?
However
And
many
why?
output tables we can have.
Okay, and how many tables can I have with 2 inputs?
16.
The 2 power n, sir.
2 power n. Okay, and what is n?
N is the number of
3.
inputs, sir.
N is number of inputs. Close, but I think you missed it. Okay. What else could n be?
Like
Number of
Binary states,
variables.
sir. Number of states, sir. You have 2 states.
Number of states. Okay. How about number of rows? What do you think about that? Okay.
Yes, sir.
So
Yes, sir.
let's kind of break it down, right? Each row can be true or false, right? So it can be 2 possible ways this table can be. This row can be in 2, this row can be in 2, this row can be 2. So how many ways in which you can make this whole table? It's 2 to the power of number of rows, right? And that's, in this case, is going to be 4 rows, right? So it's going to be 16, correct? We can have 16 possible numbers, not numbers, but operators, 2 input operators, right?
Oh.
Is that clear? So in
Yes.
this case, Shivam was right, it's 16, right? So I'll just give you an example why it is, right? Because each row could be true or false, right? And then if the first row can have two variations, two variations, two variations, two variations, and you can have all combinations, and it's 2 times 2 times 2 times 2, 2 power 4, which is 16 variations, right? So I can have 16 different unique truth tables. Each unique truth table represents one unique operator, right? Of course, some truth tables, as you can imagine, will be really silly, right? They'll be all true, right? So true, 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 true. Why is it silly? Because it doesn't care whether the input is true or false. The answer is always true, right? But that's an operator too, right? It could be always false. No matter what the input does, it's always false. That is one operator. Of course, then there could be some more meaningful ones, right? So here, I want to do a small exercise. I want you guys to help me understand what operator is this and try to explain this operator in some English way for me, right? Some logical way for me to understand this operator, right? Where false is false. True, false is false. But, this is how it is basically. So how do I understand this operator in our standard English?
If any one
You know.
of the statement is true, then
Okay.
output is true. Sorry,
Okay,
false.
if any is true, right? But then here you will see that it's false, right?
If
Any
It's an
if
exclusive
B
or
is true, if B is true, true. Otherwise, false.
Okay, you see here, this is failing here. So
If
maybe
only
Shravani.
if only
Okay.
B is true, then
So what you're saying is B should be true, but not A, right?
yeah.
Okay, hey, Shravani, you were saying something. I'm sorry. Please go ahead.
if both inputs are equal, it comes as false. For different inputs, different outputs.
Okay, how about this one?
I can say either A or B can be true, but not both. And it's an exclusive or.
But in exclusive OR, right? This statement, whichever I have written, right? This should be true. True, exclusive or false is true, right? In this case, it is false. So it is like the sort of, yes?
Sir, if A is true, then output is false. If A is false, then
Right, that doesn't work either, right? So it is basically B and not A. Of course, you can say not A and B. That's another way of saying it. Or you can say B and not A, right? So this is one way of thinking about it. That means B definitely must be true and A definitely must be false. This is the only combination that you get this, right? So let me sort of, write this, over here. B and not A. That's what this is, right? Okay, let's take a minute and analyze this one, right? So this one has all sorts of truths, right? So what do you think this is?
If both inputs are true, it's false. Otherwise, it's true.
Right, and that's okay. But is there a more? And that is correct. We are nothing wrong with that. Is there a, how do I say, more English? So like and or nots, can you just use that and so somehow explain it? Because we know that, right? So no, and is
NAND.
NAND, right?
Any of
NAND
the
means,
input is what?
so you're saying this is a NAND, which by the way also means not
Not plus and.
not and, right? So not A and B. That's what NAND is, right? Or So what is not A and B? That means if A and B is true, then take the not of that. So A and B is false, not a false, true. Again, false, false. So you'll realize that this is basically the opposite of and. And would have been false, 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 true. This is literally the inverse of that, right? So you just say not of and. So you can say not A and B. You can of course call it NAND. This is really the NAND operator, right? Also, you can say not of A and B, right? Okay, now let's continue the fun. Let's look at this last one, right? So this
Sir,
is
pardon me,
false,
sir.
false, false. Yes, yes.
And
Sir,
sir,
then say that if either of the input is false, then the
Mhm.
output is true. If
Okay,
any of the input is
so
false, the output is true.
yes, yes. That is a brilliant way of looking at it. And what is that? That means it is not A or not, oops, not B. Am I right?
Yes, sir.
Not A or not B. That's the answer, right? Yes.
Yes, sir.
And soon we will learn a theorem. It is called De Morgan's theorem, and we will go over it. That will basically prove exactly this, that not and is the same as not A or not B. And this is what De Morgan theorem says. So that means A and B, the whole thing not, is equal to A not or B not. I mean, not of B. Exactly. So, yep, Navid, you're right. You can also say it like that. And that's also absolutely correct. Okay, sorry, we were going to the last one. I'm so sorry. Good point, Navid. All right, so last one. Anybody can quickly tell me what it is?
AND gate.
Sorry, what?
AND gate.
and yet,
AND gate. This is a simple AND gate, right? Straightforward. So what you'll realize is, I mean, it's not necessary for us to describe everything back in English, but the cool thing is you can represent operators using this truth table. It uniquely and clearly specifies how that operator is going to work. And, we can be very clear about it. So this is one sort of very clear way of specifying an operator. Now, of course, we worked with two input operators, right? How about making things more interesting, right? So how about three? This is two, right? How about three input operators? Heck, four input operators, right? Now you'll realize that, okay, the English is going to only last for so long, and then it's not going to work anymore. It's just too complex for us to write this in plain English, because this is combining four, statements of four variables that could each be either true or false, and then we combine them. Of course, the number of such four input operators are going to be 2 power 16, which is quite a lot, right? And but there can be that many different types of operators and so on. So the main point is, as the number of inputs increase, right, the complexity increases. And believe it or not, you will find in your designs data, of course not yet, 25 or 30 input operators. Now imagine doing and or to it, right? It's going to drive you crazy, right? So that's why you need math. You need some math to help you understand how to work with it, how to simplify it, how to deal with it, right? And that's the Boolean algebra. Having said that, I'll cover to some extent, and then we'll sort of briefly cover the high level things of what it is, but we will not necessarily do operations that involve 25 or 30 input vectors, because that will be really complex. So that stuff, we better write scripts or code to sort of analyze it for us, right? But these are there in designs. Actual designs routinely will have these many inputs that the code needs to work with. So, but for our class problems, don't worry, we'll try to limit it to 4, 5, 6 inputs and not go crazy on it, right? So how do we deal with more inputs a bit more efficiently, right? Because if I see this table, you can be sure that, I'm going to get brain fog. It's not going to work for me, right? And if you did add one more input, honestly, I'm just going to stare at that and my mind is going to blank itself. You can say whatever you want after that, nothing is going in. It's just blank, right? Of course, that makes sense. It's just like so many trues and false, right? It's not making any sense at this moment. With 3, I can still struggle and do something. With 2, I was comfortable. 3 is maybe okay. 4, it starts to get really, really tough. Almost something I can't really tell very easily. So this is not a great way to understand things, right? Can I make it slightly better, right? So what you'll realize is this is very linear, right? I have kind of things happening in only one dimension. So what if I try to use more dimensions, right? So that's what brings us to our next tool. It's called the Kano map. Of course, I'm sure you've heard of this and you may have seen this. And if you have not seen this, that's perfectly fine. So let me go over it, right? There are some special things. So it's kind of the same thing, right? So the truth table had 16 values, 16 rows for 4 inputs. Now I have a 4 input Kano map. I'm representing A, B along the different rows, and I'm representing the variable CD along the different columns. Okay, because now I have rows and columns, instead of having 16 long rows and really trying to understand them, I now can work with a small grid, which visually I can work with better, right? And now I'm also starting to do something that I didn't do before. I'm just starting to represent 0 for false. Okay, so I just arbitrarily called 0 is false. Oops. And 1 is true. Okay, so instead of writing so many letters, I'll just write 0 and 1. Okay, in any case, I'm going to be representing it that way. So might as well start working with it, right? So when I say 0, 0, what I mean here is A is false and B is false. A different way of saying A is false and B is false is to kind of say A bar and B bar, which means, I mean, basically whatever makes this statement true is what this line is, which means A is false and B is false. That's how you get here. So you can write it as A bar, B bar like this, if this makes it better for you, or you can write it in this way. Hopefully it's the same thing. So when it is 0, it means that variable is false. If it's 1, means that variable is true, right? The one more thing you will notice, which is intentional and not a typo, is I have actually gone from 0, 0 to 0, 1. Instead of going to 1, 0, which would have been an increment, right? I actually went to 1, 1 and then 1, 0, right? And the reason to do this is I'm following something called as a gray code. In a gray code, what I'm doing is I'm only changing 1 digit at a time. So from 0, 1, if I had gone to 1, 0, I would have changed both variables simultaneously. And I didn't want to do that. I wanted to only change one variable. So since I had 0, 1, I could have either gone to 1, 1, or I could have gone to 0, 0. Turns out 0, 0 is already covered. So I went to 1, 1. Now I can come back to 1, 0. Okay, so this way or this sequence of writing it, it's called gray code. So the speciality of gray code is only one variable is changing at a time. And later you will see why it's required and why it makes sense in Kano maps to try to follow gray code. Because when you simplify things, right, you will notice that this gray code is, how do I say, really helpful, right? And we'll talk about it. So, but first I want to make sure that we are very clear on this thing. First of all, I hope all of you can see that this is basically the same information as a truth table, just in a different format, right? I hope you can see that. There's nothing that was in the truth table that is missing, or there is nothing new in this that somehow wasn't. It's just a different way of representing it. And once we represent it in this way, as humans, we can see patterns better, right? Instead of looking through many, many, many rows and trying to look for patterns, by looking at a grid, we can find some patterns to try to see what's happening, right? In this case, maybe the patterns are less, right? But let us say if I make the same kind of grid, right? Assume I had the same thing. And I'm not going to write zeros, I'm just going to write ones, right? Suppose I had like this, 1, 1. Suppose this is how it was, right? So 0, 0, 0, 1, 1, 1, 1, 0, right? And if I had ones only in the middle, right? So what can I simplify it to, right? So you will find that, hey, look, it's really weird. When I change C from 0 to 1, it makes no difference to the output. Looks like the output doesn't care about C, right? The output absolutely wants to make sure that D is 1, right? And on a similar way, it absolutely also wants to make sure that B is 1. Because in the same way, right, you'll have 0, 0, 0, 1, 1, 1, 1, 0, and B is 1 only in these two cases. So what you will find is, look, whenever B is 1 and D is 1, my output is 1. Everywhere else, it's not, right? So really, this thing is nothing but B and D, right? And believe me, figuring this out from the truth table would have been insanely difficult, right? But now we were somehow able to see this pattern. So what we are doing is we've actually combined this into this big chunk, right? And when I have a chunk of 4, right, it means I can eliminate 2 variables. If I have a chunk of 2, right, let us say this was 0 and this was 0, then even with a chunk of 2, right, I can eliminate 1 variable. So can someone tell me which variable I can eliminate in this chunk of 2?
B.
B, you're very close. It's not B because B is 1 in both cases, but you're really close. You want to try again?
A, sir.
A, correct, A. Because A was 0 here and 1 here, and it made literally no difference, right? So basically A can be gone. So, but for this to be true, B has to be true. And turns out C has to be true because it was 1, and D has to be true. So this is something like B, C, D, or B and C and D. That's what this 1 and 1 would mean, right? So of course, now I will try to maybe erase all this and maybe give you another problem to work with. Now let's say I have this Kano map. Okay. Anyway, like I said, I'm not going to write the false stuff. I'm only going to write true, right? So let's say I have a true statement where I just have this true. Everything else is false, right? So what does this box represent? Anybody? So of course, like just so you know, this was
A bar, B bar,
A
C
bar,
bar,
A
C.
bar,
A bar, B bar.
B bar, C bar, D bar.
Yes, it's A bar and B bar and C bar and D bar, right? It's the AND of all 4 is this, right? So if we also had this, right? Let's now try to write this. So basically if I have 2 true statements, right? Then it's nothing but OR. Please allow me to write OR as a plus. I can of course write it as an OR, which is okay, any symbol OR. Please help me what this is. So just for your
A bar,
reference.
B bar, C bar, D.
A bar.
B bar.
B
This
bar.
is AB, right? Please be careful. This is CD.
A B bar.
This is AB.
Yes,
This is 0, 0, 0, 1, right?
Okay.
Okay, please tell me A bar.
A bar B, C bar D
A
bar.
bar, B, C bar, D bar.
Perfect. So if I had this or this, what does it mean?
B can be eliminated.
Correct. A bar, C bar, D bar. So you'll find that this or this is nothing but this, right? So there is some math that we can do where we can simplify these things. First of all, each element or each thing here is some combination of AND of A, B, C, D. It could be A or A bar, B or B bar, C or D bar, depending on which place you are, right? So it is that unique combination of A, B, C, D in AND format, right? And then all of these are nothing but that, whichever is true, right? And when we combine adjacent ORs, right, we find that we can start eliminating variables. If you have a block of 2, you can eliminate 1 variable. If you had a block of 4, you can eliminate 2 variables. If you had this block of 4 also, you can eliminate 2 variables and so on, right? And of course, you can have blocks of 8. In this case, you can eliminate literally 3 variables, right? So you could have that. And then we will, certainly cover the math for it next class of how this works out and why I'm able to eliminate all this. But now you can see why I wanted only 1 variable to change at a time. So that if I had this, right, or any sort of square box, I knew that only 1 variable changed between this row to this row. If two variables change, everything would not work anymore, right? So for us to use Kano maps in this way, make these kind of little, boxes and simplify things, right? We need to use this gray code. That means from one row to the next, only one variable can change at a time. You can't change both, right? So long as you do this, then we can start using this Kano map to somehow simplify the expressions and write the expressions back in terms of and, or, and not. Why? Because these, operators come naturally to us. We have understood them over many, many years of life and schooling, and now we understand them really well. So we find it always easy to kind of put it in that way. So we will be converting. This is called sum of products. Usually the and is called a product term. So if I say A and B, we usually write A, B. You can think of it as I'm multiplying A and B. It's not really like a normal multiplication of numbers, but it's a little bit like a number because, 1 into 0 is what? Is 0. 0 into 1 is 0. That means if any one of them goes 0, the answer is 0. So in that way, if you think of it in that way, right? The and is a little bit like multiplication for binary, single bit binaries, right? And then what is a not? A not, sorry, not, or it's not really addition, but it's a little bit like addition. Let me explain it to you. So if you have 1 or 1, let me write all the expressions, right? And then there should be, first of all, if I'm adding, right? Forget about the or part. I would get 1, I would get 1, I would get 1. This is straightforward, right? Only confusion would be this guy, right? This will actually give me 2. Did I miss something? Did I write something again? Sorry, it should have been 0. So 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1. The only confusion would be 1 plus 1. If you can sort of think of this also as 1 or greater than 1, however you want to think of it, in some way you can start seeing ORs as some kind of sum, right? So basically this expression, when we write it as, A bar B, C D bar plus B bar C D, this is a product and this is a sum. So this is a sum of many products. There's going to be many, many products and I'm going to sum it up. It's called sum of products. What is product of sums? Product of sum means there should be a giant product and inside each should be a sum. Let's see, A bar plus B plus C bar, whatever it is, right? This is called product of sums. Okay. So usually we like to write expressions in the sum of products. It helps us to understand this. And using this Kano map techniques that we will cover more next class, we are able to reduce and optimize these expressions to be the minimum expressions. So we will cover this Kano map optimization. We'll also cover something called as De Morgan's theorem in next class, right? So those are things we're going to cover. With that, I think we'll get a good handle on what exactly is some handle on Boolean algebra. Then we'll start doing two things, seeing how circuits can implement logic functions. And then what else can I do with logic functions? Can I make an adder with logic functions? Sounds really silly, but you'll be surprised what you can do, right? Can I make a multiplier with logic functions? Wait a minute. A multiplier is like, I have a 1, 0, 1, 0. A multiplexer too, but also a multiplier, right? So can I make this, right? So a circuit that calculates the product of two numbers, two binary numbers, right? Using only logic gates. You'd think that that's really silly, but that's actually possible, right? So I just wanted to, first we'll cover the math of how to work with logic. Then we'll talk about how you implement logic using circuits, right? And once we understood that, next we'll try to see what can I do with this logic gates, right? What and all can I implement? Okay. And like I said, you could do all sorts of crazy stuff with them. So, and we'll cover those. Before I let you guys all go, I have one question for you. There's been a request from several students that if we can class the start half an hour later, that means have the class from 7 to 9 instead of 6:30 to 8:30. That's because, you know, some students are working or have college or whatever, and by the time they get home, it's a bit tough for them. So if any of you have a strong problem with that, you can let me know. You can, you know, somehow let us know. You can let me know right now. If not, if it's okay with you guys, just to accommodate some of those other students who are missing out more of the classes, I think we are flexible. We can move it 7 to 9. Or we'll do one thing. I'll even see if there's a way we could send out a survey or something. But ideally, the point is if we can accommodate for those other students who are not able to make it, then so long as it's still doable for all of you. Because the reason I ask you guys is because you all did make it to class. So I'm really happy about that.
Yeah, yes, sir. Please take class from 7 because as I am a working professional, so
For you, it's easier. Yeah, sure. So we'll also try to send out a short, just to make sure if any of you have a huge problem, you can let me know. But otherwise, we'll at least start 7 to 9. The cool thing is, even in the worst case, you sort of heard the class for 1.5 hours and you had to leave half an hour, you know, near the end. It's okay because you can catch up. Usually, if you miss the first half, sometimes we are building up concepts on top of each other. And if you miss sort of the first part, then it's really hard to kind of catch up and make sense of the rest of the class. That's why we also wanted to somehow accommodate. So we'll check on this, but if it's okay from most students, we will update it. Hey, I know that you know, Dr. Krishnakant was really good about setting up your homework ahead of time. So I was not able to do that today, but I will certainly upload it tomorrow. Meanwhile, I'm going to make you know, homework in LMS right now, where I'm hoping that you are doing this before. You will be required to submit your class notes. Just take quick pictures of whatever notes you made, right, and submit it. Doesn't have to be detailed anything. Whatever you made notes, right, that just helps us to understand, you know, what you were doing, and just submit those notes for the class. You can just do it tonight itself. Just give me a couple of minutes. I'll quickly make that homework. We'll do this for all the classes, and then of course the actual homework problem that I would like you to kind of work on, I will try to upload it by tomorrow. Okay. And the main thing is this first week, we may or may not, we'll see if we get there, we may or may not cover doing designs. I know I sort of started off this whole lecture with a big design thing, but I'm hoping that at least from the next week, we'll absolutely start doing design problems. So just 1 week, we'll cover some math, some discussions on what is possible, what are things, what are there, right? And then from next week, you know, I really would like you guys to do your designs. Okay. And by the way, the design methodology, whatever I told you, right? It's not only true for digital design. If you were doing analog design, it would look very similar. Probably instead of you know, the control, and instead of some there, you may have some slight analog things which can be modified, but you'll still follow kind of a similar way for doing analog designs as well. So whether you do analog design or digital design, or you do verification or any design process, right, that breakdown will look very similar. Okay, any final questions? Okay, so great. Hey, next we'll go deeper into Boolean algebra. And, you know, please don't hesitate at all to ask all sorts of questions. I really like the class today. And thanks to several of you to actively participate. Naved, Mohammed, there was Veera, and many of you, right? Shravani, you all did great, and Rajita, and so on, right? So thank you, and Jonathan. Sorry, I forgot. So yeah, please, you know, I want more such participation. It makes it much more fun. So we will continue from next class. Meanwhile, I'm available for another minute or so if you want, if there's any questions. And soon after I close the class, I'm going to upload that homework, which is pretty straightforward. Just take pictures of your class notes and upload it. Yes?
Can I ask about the reference books to practice more?
Yes, reference books. Okay, that's a good one. I will try to find you good reference books that will have more
I
problems.
have a book like digital electronics from Triple branch in diploma.
Okay.
It is
So
more.
if this book is available online, right, I strongly recommend you to post, or if there is a way to.
I'll make sure you to post that.
Okay. Yeah, please post it. And then one is you can post it in the LMS, or if you want, you can, kind of let me know. I can, download it and upload it back to the LMS to make it easy for people to.
Sir, actually, I have a short notes about digital electronics, which I have studied, and I made a short notes.
Okay.
It's a bit easy, to solve number systems, decimal to other number system and other to decimal number systems. Instead of decimal to decimal to hexa.
Certainly. So, whatever reference material you have, right? Please, either you can share with the class or you can share with me. I will upload it, right? And I will also certainly find some more. And and this I strongly believe, right? I don't think I know of all the material and all the ways that we could do things. I know some ways, and I'm happy to share those and explain it. And I'm certainly open to other methods. So please feel free to share your thoughts and ideas, and that's really good. So yeah, please either you can in LMS you can actually post messages or post questions. I'm not sure if you guys know how to do it. If not, I'll see if I can find a way to have a very short, not to take much time, maybe a 5-10 minute LMS training just to show you a few things. But you can certainly post things and discuss with each other on LMS, kind of like, chatting with each other, except it'll be visible for the whole class and the teachers, so we can also comment and review it. And on the other hand, if it's some material you'd rather want me to post it for the LMS, I can download it and upload it or something. So that's we are certainly open to that. And I will certainly look up. We do have lots of references. I can share some standard textbooks that you can refer, and or if I find some online references. And some of you may or may not have heard, there is one of my very favorite reference. It's called HDL bits. HDL bits. I'll send you the links and all. You don't have to worry about it just yet. That's a brilliant website. It's a brilliant piece of work by some people, and I really appreciate. So that really will help you learn very long when we get to that. So just give us a couple of weeks to get to that point, right? And that I would strongly recommend you to really go through. They have a very, very long problem set, and I want you to solve each and every problem in that. Absolutely, every one of the problems you should solve. It's a requirement, right? And it's really fun. It's a lot of design problems where the first design problem is literally a wire. So you just connect the input to the output, and that's the solution. That's all it is. So it starts with a simple wire. Of course, it goes on to having interesting gates, and then it moves on to being something quite complex, like, with lots of flip-flops, really complex designs, right? That you can do it. The cool thing is you can write your design. In that case, they only accept Verilog, right? So you can write your Verilog code in there to describe your hardware. And it can verify it. They already have a test bench. They will run the test bench on your hardware. They will let you know that did you design it correctly, or if you made mistakes, right? If you made mistakes, you will see what went wrong. They'll show you the waveform where you went wrong, so you can go back and fix your code, right? So it's really good to practice and learn. So that is, of course, relevant once you learn a bit of Verilog. Until then, I'll try to find other textbooks and other things for you guys to kind of practice. Okay.
So one
Good question.
last question.
Yeah.
It might seem out of the box. When I was working today, I found out something about like we are using some flash memories, which is based on NAND flash. So
Okay.
I came across a term called NAND flash memory, and along with that, some DDRs and EEPROMs they're using. So I just wanted to know what like a NAND flash do and like different
Okay.
between the EEPROMs. So that kind of memory which we will be dealing with anytime.
So basically, right, I can tell you what a NAND flash is, right? So NAND flash is a piece of non-volatile memory, right? I have myself worked on some NAND flashes that I was previously at Micron for a while. And so I have certainly worked on those memories, right? So it is a non-volatile memory. And non-volatile means what? Non-volatile means if I turn off the power, right? The memory will still remember, it will retain its state. I can turn off the power for many days and I can turn it back on. It's like our hard drive, right? Even if you turn off your laptop, you remove all the power, it remembers, right? It's not like the data just
Yeah, I was
vanishes.
going through the data sheet. It was telling about like 1 to 20 years it will retain or some kind of.
Right. It's usually, yeah, they are required to keep it at least for 10 years. Otherwise, they don't qualify as a flash, right? Now, there's good and bad things, right? So the bad thing with a NAND flash is that it can't really, it gets worn out fast. So what is meant by worn out, right? If you keep writing to it, right? If you keep writing to the NAND memory, if you write it enough times, maybe 100,000 times or something, it will stop working. That's really bad, right? So, oh shit, you wrote enough times to an address and it stops working. So, you know what usually companies would do is you would have a bunch of electronics sitting in front of it, which will take your read and write instructions, and they will keep track of which address got written how many times. And if you write to some address too many times, they will quietly copy that data somewhere else and point that address to that new location. So you will think that you're writing to the old location again and again, but internally the address got changed. Now it is writing to new address. This is called where leveling. So this is an algorithm that the electronics will automatically be running. So it will actually maintain a table of all the address translations. That means external world thinks this is the address. Really, this is the other address, right? But this is to deal with this problem of the memory having finite number of write cycles after which it fails, right? So you will not notice it, but the memory will manage itself. And what will happen in a NAND flash is after multiple use, the size of the memory will start shrinking. It's not like why it is shrinking is certain areas are now not reliable and you can't write anymore. So automatically the controller will remove it. So you may start out with a 32 gigabit memory or whatever gigabyte memory, right? And it may slowly become 31, 30, so on and so forth. But that 30 gigabytes will be working properly. So basically it's a non-volatile memory. How it works actually is you sandwich a piece of conductor between two insulators. The insulators are oxide, okay? And you store some charge, you store some electrons in that insulator. Those electrons have nowhere to go. Basically, they are insulated on all sides. So the only way they can get out of there is by some sort of leakage. And that leakage is going to be very small. So basically, within a matter of 10 or 20 years, you don't lose those electrons. So that's how you save that information. And the way you read it is actually this electrode is sandwiched inside the MOSFET, inside the gate. So, you know, usually if you know how a MOSFET looks, there's gate, there is oxide, metal oxide, and then there's a channel, right? So in that between the gate and the channel, there is this sandwich of oxide, conductor, oxide. This floating conductor stores that charge. It actually stores electrons, right? And that's how it can change the state. Once it has electrons, the threshold voltage of the MOSFET will be different. If it has no electrons, the threshold voltage will be different. That's how you can tell whether there are electrons or there are
That's
no
where
electrons.
the electrons are there, like in the channel between source and drain.
No, they are
channel
not
between-
on the channel, right? Because if they are in the channel, they will easily get leaked off. They are on an conductor sandwiched inside the oxide. It's completely surrounded by oxide everywhere so that the electrons have nowhere to go. They are literally inside that, how do I say, insulated They're insulated from all sides.
Okay.
And there
sir.
is one more flash memory called NOR flash, and that's just how they are connected. So if you connect many cells in series, it's called a NAND flash. If you somehow connect them in parallel, it's called a NOR flash. So you have NOR flash and NAND flash. The basic flash concept is the same, but how you connect it, how you read and write is slightly different. And usually, and both are used, right? So NOR flash is used mostly as boot up memory for most computers, whereas NAND flash is used as the SSD drive for most
Yeah,
computers.
solid state, yeah.
Yeah.
Got it. So
Sorry for this digression.
Yeah, the construction and all, like it's like totally different. Like MOSFET, if the channel is formed, then the current will be flowing, right? So then you'll have losses. So here you told it will be stored like on the all four sides, all 360 degrees, it will be stored as an insulator, right? Like the charge.
Correct. That conductor is surrounded by insulator. There is no nothing touching it, right? So of course, someone may ask, how did the charge get there in the first place? If
Yeah.
it was insulating everywhere? There is a phenomenon called quantum mechanical tunneling. I won't cover that, but it's the electrons get there through this quantum mechanical tunneling. And why they cannot get out with quantum mechanical tunneling, again, more physics, I can cover it. But let's just say during write, you create conditions to make quantum mechanical tunneling happen. And then during the standby period, the tunneling can never happen again because the voltages are somehow different. So, but anyway, that's how it works. So even if that piece of conductor is completely surrounded by insulators, you can still put charge into it through this mechanism called quantum mechanical tunneling. But once you put it, unless you induce the conditions of quantum mechanical tunneling again, there's no way for the charges to get out. That's why until you write again, the charges are going to be there.
Okay. So you told it the one term you used, right, sir? What is like how it will identify and it will like store in a different memory? I just missed that.
Where leveling.
Where leveling. Okay.
Yeah.
Like normal wear and tear, that where you're telling, like
yes,
correct.
Okay. So you don't want to write into one address too many times. You want to write to uniformly kind of spread the, how do I say, the damage, so that it's not like one address just stops working. You just let more and more addresses sort of be there, and then when a whole page or when a whole chunk fails, then you discard it and sort of copy that page over somewhere else.
Okay. So this like it will identify like this mechanism, the microcontroller, they'll already like after in the aging factor that happens, right? Or how do they estimate?
Yeah, and there's ways, right? It's a design problem. How do I figure out that the memory has gone bad? Once it has gone bad, what should I do? How do I save it? It's exactly a design, right? So you figure it out. When that happens, you trigger something, you copy and move the memory, and you do all this. You design it in hardware or software, and you make sure it's working. Then that's part of the controller then.
Thank you, sir. Yeah, I just going through some material.
Sure, there's a lot of stuff, right? And don't worry if it's good to be curious and learn more, but also I would say don't worry if you're not fully understanding some really complex stuff. These are things that you will understand much better sooner or later. So if you didn't catch any of what I said, no need to get worried at all. It's perfectly fine. You'll learn all this in due time.
Okay. Thank you, sir. Thank you, sir.
Welcome.
Thank you, sir.
Okay, guys, you have a good night. Sorry for keeping you up for some extra time, and then we'll continue this from next class. So I'll quickly make up that homework where you need to submit your class notes. Please do that today itself. Thank you.
Thank you.
Excuse me, sir.
Yes.
Sir, you have said that the previous canvas designing example, right? The switching process. So you will upload it in a class notes, or you will make a another file for having it.
Okay. You mean to say these slides?
No, sir. You said about example problem.
Example solution.
Yeah.
Okay, so I'll do one thing. Right now, the example I wasn't planning on uploading, but I think given the comments, I will also upload the example to today's class notes. So I will certainly upload this presentation, but on top of this presentation, I'll separately include a small PDF that will have that one example that we discussed.
Okay. Thank you, sir.
Sure. Hey, and please write, that is, like I said, design is a bit of a personal process, so there is no right and wrong. Please don't think that that's the only way to do the canvas. You can, I mean, the points and the structure needs to be the same, but you can certainly do it, more ways. I will upload it. Okay, great. Hey, see you guys then. Maybe we'll of course communicate ahead of time. We'll see if it's possible. Then next Thursday we'll maybe meet at 7. If that's more convenient for everybody, then we'll do that from 7 to 9. Okay. Thanks. Thanks everyone.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thanks.